Now, once this is done, if we look at the show MPLS forwarding table, just like we would in LDP, what we should see here is that there's an interface that now has a TE tunnel, or there should be a label here that is associated with the tunnel. And actually, it may not show up there until I go to point a route out it. So let's look at the show MPLS traffic engineering tunnels. And what we're looking for here is two things. The path needs to be valid, and the signaling needs to be connected. Okay, again, a path calculation is going to happen first in terms of computing constrained shortest path first. Then the signaling is going to be for RSVP. There's separate verifications we need to do because there can be an error in RSVP, but the path calculation was correct. Or vice versa. I wasn't able to calculate the path, which means that I wasn't able to signal the path. Okay, there's a question here, actually a really good question, is there a tunnel configured on the other side? And as of now, the answer is no. The reason why, and this is a big difference between RSVP for traffic engineering versus either LDP or for BGP, and the key point here is that traffic engineering forms unidirectional tunnels. So router 1 has formed a tunnel outbound to router 3, but router 3 has not formed a tunnel back. Now, if we look at this from our other applications point of view, like layer 3 VPN or layer 2 VPN, we know that that's not going to work. Because if I'm not using a label switch path to you and you are not using a label switch path to me, traffic is going to get dropped as it goes through the core of the network. Now, in this particular case, I already have the LDP enabled with ISIS. So router 1 is going to be using a TE tunnel outbound, where router 3 is going to be using an LDP tunnel back. But just as we saw previously with LDP versus BGP, in the data plane, there's no difference between an LDP signal tunnel versus a BGP signal tunnel, or likewise in this case, versus a TE signal tunnel. Ultimately, what we're trying to do is to populate the MPLS forwarding table so that we know when we go to the particular destination, that should tell us here somewhere in this output, is what is the label number that we are using. And I think it actually is not going to show this until we go to route out it. Okay, what I mean by this is that if we look at the routing table and it says to get to 3333, notice that we're still using our physical interfaces. So like I mentioned before, this is the same as like a regular GRE tunnel. Just because you configure the tunnel doesn't mean you're actually sending any traffic out there. You would need to configure dynamic routing on it, like OSPF or ISIS, do static routing, do policy routing, some sort of routing method in order to force the traffic to that interface, or more specifically to install it in the RIB, which is the routing table here. Now, we'll see this in more detail later as we start to get into more advanced examples of how specifically can we route. But for this example, we're going to do just the most basic variation, which is going to do just static routing. So we're going to say for the destination 3333, we're going to point it to interface tunnel 0. I believe this is what is going to actually create the label binding because we're not using it in the label forwarding information base. So as we talked about previously, like BGP and LDP, you might be receiving a label from both of them, but you won't use the BGP label until you have the route installed as a BGP route. So same is true with LDP. If I'm learning the route through BGP, I cannot use my IGP learned route, which is LDP, where in this case we are learning the route through traffic engineering, but it's not actually installed in the RIB, in the forwarding table. So simple solution for this. On router 1, we're simply going to say to get to 3333/32, we're going to use tunnel 0. Okay, if we now show IP route, we should see now we have the static route installed. It says it's pointing directly towards tunnel 0. If we now look at the show MPLS forwarding table, we should now have a tunnel label installed, which I believe in the previous output. Let me remove the static route. And then let's do show MPLS forwarding table, pipe to include capital T. Right now it says, actually no, I wanted to remove the route. No IP route. Okay, so now we can see it's not using the tunnel label. So once we actually install it in the rib and the fib, now it installs it. Okay, it doesn't actually tell us what the outgoing label value is, because from router 1's perspective, it thinks it is directly connected to router 3. So we'll see a little bit later when we talk about penultimate hop hopping, PHP, and how this relates to the TE tunnels. There are some problem cases where we can run into a black hole in the middle of the network if we're not including enough labels on the top of the stack. Okay, but just for this basic example, if we now look at the show MPLS traffic engineering tunnels, we should see that there is a label number somewhere in here. Let's say traffic engineering tunnels, what, maybe it's in the detail output. No, it doesn't show it here. Maybe XE does not show this. What we can look at is the show MPLS forwarding table for the destination. In our case, destination is 3333, and we want to see the detail. Label number is 37. So this means now if we do a trace route to 3333, and we source this like from our loopback, we should see it goes out the tunnel and it's using label number 37. Now, if the tunnel was down, okay, so we revoke the TE tunnel from the routing table. This means that the static route gets withdrawn. We fall back to our dynamic route, which in this case is coming from ISIS. ISIS is then going to use the LDP associator label, which we see is going to be a different number. So if we look at the forwarding table for 3333, it says now we're using label 16,007. So if we do a trace to it, this was the original label that came from the LDP process. In this case, we're actually using two different labels because we are doing ECMP pointing us in this direction here, and then in this direction here. But point being is that once the tunnel is enabled, we're only going to use the tunnel label. Okay, now we got label number 41. So the label number is changing dynamically, just like in the case of LDP or BGP. Every time the interface comes up, you do a negotiation between the peers. I negotiate with the next hop, which in my case is router 2. We're going to use label number 41. Then router 2 likewise says between me and router 3, I'm going to use a different label number, and it's pushed, swapped, and popped, just like we have in a normal MPLS data plane operation. Now, in order to figure out how specifically are we routing the tunnel, though, we can see the exact verbatim path if we're actually not the verbatim path. That's bad terminology. That's a different term I'll talk about later. But we can see the what is the actual path of the tunnel if we show MPLS traffic engineering tunnels, and it's going to tell us what specific hops are we going through. Okay, so it says we're starting at me, which is router 1. We're going on my link, going to router 2. Then from router 2, we're exiting its link and going to router 3. Then from router 3, it itself is going to its own loopback. Or actually, no, 13 is, which guy? 213 is going in, looks like it's going in this direction. Okay, so it's going to router 2, then from router 2 it's going to XR3, and then from XR3 it's going to router 3. Now ultimately the way that it picks this though is simply based on the IGB path. So there must be something that's going on in ISIS in the middle that's causing it to choose this path. I think at the core of the network some of these interfaces are actually just disabled. So let's look at the show IP interface brief and pipe to include admin down, which is, that's what it is. So from router 2's perspective, that link over to router 3 is shut down. So if we go to router 1 and do a trace route, let's trace to 3333, source from our loopback, we should see it's going to go from 1 to 2 to XR3 and to router 3, but point being is that it is following a labeled path. Now if the interface here is re-enabled, we're going to now take 2 hops to get there, as opposed to taking 1, 2, 3 hops, or in other words, simply based on the shortest path that ISIS is calculating. Same would be true with OSPF. If all of the links are equal bandwidth, it means they're equal cost, and effectively the IGB metric then just becomes a hop count. So from router 2, let's go to the physical link, or in this case, the logical link, and no shut the port. Okay, we now have an ISIS adjacency, and from router 1's point of view, we should see the tunnel is going to re-signal because there's going to be change in the underlying IGP topology, and we should go from 2 to 3 directly. It's going to take a minute for it to actually do the recalculation. One way that we can force this, the simple way, is just to shut the tunnel down and then to no shut it. So every time you flap the TE tunnel, it causes to recalculate the path and then to re-signal the path. Otherwise, if you leave the tunnel alone, there's a timer value you can configure in order to get it to recalculate, but I think the default value is something like a half an hour, which is it's some sort of long timer value. Okay, so now if we trace to router 3, we're going directly from 2 to 3. Okay, so let's look at from the middle then, how are the other devices in the path figuring this out? So from router 1, it's asking the rest of the topology, can you build me a tunnel over to router 3? So this is assuming that when router 1 does a lookup, and it says show MPLS traffic engineering topology, that we know about the node that is 3333. It says, yes, that device is running TE. Okay, these are the particular interfaces that it's running TE on. These are the attributes of the links, which again, we'll come back to later. But what is important about this is what is the interface address, and then also what is the neighbor's interface that we are directly attached to. Okay, now in this case it says the neighbor node identifier is this. This is some sort of internal pointer that's mapping to the particular router that it's connected to. But the overall logic of this is it's describing the shortest path tree. Or not necessarily the shortest path tree, it's describing the link state database. Is to say router 3 is connected to router 2 is connected to router 1. These are the metrics that are associated with the links, hence that's how I shelve the shortest path tree. We'll see that when we change to OSPF, it's going to be the same thing. That we first build the OSPF link state database, we run through the constraints, like what bandwidth do we want, whatever, then the end result is we have the shortest path tree, but based on those specific additional calculations. So in our case here on router 1, since we basically didn't ask for anything, any other constraints, the way that the tunnel routes is going to be the same direction that the normal shortest path tree would. Okay, now there's another interesting question here, which is kind of what you would think is a logic problem, is that I'm pointing the tunnel destination out the tunnel, and the tunnel is pointing to that particular destination. Normally you would think that this is a recursive loop, because if we look at the tunnel config and we look at the route, it says to get to 3, use the tunnel. To get to the tunnel, go to 3. So it looks like that these two routes are pointing back to each other as an infinite recursion loop, which would be true if this was a regular GRE tunnel, but in our case it's not because we're using MPLS labels in order to get there. Now we'll see a little bit later when we look at some more advanced routing examples over the tunnels, you don't necessarily need to route the destination of the tunnel out the tunnel. You can use the tunnel for other destinations. So what I mean by this is that we could form a tunnel that goes from, let's say, router 1 to XR2, that we go this direction. And we say over this tunnel, I'm going to use it to route to get to XR3. Or I'm going to use it to route to get to router 3. And in a real design, this is very common in the core of the service provider network, that we do P2P tunnels or PE2P tunnels that we're using for the point of either link or node protection. The idea being is that if I configure tunnels as a full mesh between all of my PEs, we run into that scaling limitation, same as like if we have a full mesh of IBGP, that we have n times n minus 1 over 2. So it means that if you have, let's say we have 100 PEs times 99 over 2, it means you'd have to have like 5,000 tunnels. So in most practical cases, it's not feasible to have a full mesh of traffic engineering tunnels. This is why you can use TE for some portions of the network, but not everywhere. But you can combine the tunnels together. Okay, so what I mean is that we might be having, let's say from router 1 over to router 3, we're going to use LDP to exchange the labels between them. But as I go into the core of the network, let's say I route this direction, XR1 might have a tunnel going between these two guys that is formed based on traffic engineering. So XR1 is basically going to say, I want to make sure that if I'm going to XR3, I'm going to go this direction first. But if this interface fails, I'm going to pre-calculate a backup tunnel that's going this way. From router 1's point of view, that's using LDP to reach router 3, that's going to be transparent. It simply says that I have some sort of label that's going in this direction. When XR1 gets it, it's going to say this is my primary path, but if I learn that this interface goes down, I'm then going to send the traffic over the secondary path. So again, in terms of the static route pointing towards the destination itself, it is valid in this case for TE, but it's not valid in other cases, like when you're using GRE. Okay, let's also see this from iOS XR's point of view. Logic is going to be really similar between the two of them. So in the case of XR, there is a specific tunnel type that is for traffic engineering. So we're going to say here at the top, okay, first let's look at our current path. Let's say show IP route for 3333. We should be learning this through IGP. If we show MPLS forwarding table, we should be learning an LDP label for the destination, which is this one here. We're using number 31. It says the outgoing interface is towards router 2. Okay, so right now it's routing in this direction to get there. It's 2 hops away. So if we do a trace to 3333, we should see that we're following a label path over router 2. Okay, right now we're using label number 31. Okay, but now we're going to do a TE tunnel. So in global config, we're going to configure interface. And if we look at the question mark here, this is going to be tunnel TE. Okay, tunnel traffic engineering. So interface tunnel TE, we give it a number, okay, like tunnel 0. We specify what is the source, which is going to be our IPv4 address. So IPv4 unnumbered is going to be coming from our loopback. We specify what's the destination. Destination is going to be router 3. And what is the path option? Okay, so how are we calculating the tunnel? We give it a sequence number, and in this case, we're going to say dynamic. So in other words, there's no constraints. We're just saying as long as you have a path to router 3, that's going to be the valid route that we're going to use. Okay, if we then look at the, let's do a commit, we should get a log message that the tunnel is going to come up. Okay, depending on what our syslog level is, I'm not sure what level we're logging at right now. But let's look at the show IP interface brief. We should see tunnel is up. And if we show MPLS traffic engineering tunnel, so same syntax as it is in regular iOS, same outputs we're looking for here. The path is valid, the signaling was connected. If both of these are true, the end result is that the link is up. If we see that the link is up-down, the line protocol is down, that's either an error in the calculation, like I couldn't reserve the amount of bandwidth, I couldn't find the affinity or the link color, or it could be a problem in the signaling like RSVP failed. But the rest of this output should be the same basically as we see in regular iOS. It should tell us what is the explicit path that we're using. So we're going from us to router 2, then from router 2 to router 3, this is where the destination is. Now if we look at the MPLS forwarding table though, we're still not yet using this as the destination because we didn't configure any routing towards it. So we either need to configure dynamic routing like enable ISIS on the link, or we can do just a static route to say to get to 3333, we're going to use interface tunnel-TE0. Or in the case of iOS XR, globally this would be under router static. Destination is going to be under address family IPv4, IPv4 unicast, and 3333/32 is via tunnel TE0. Okay, if we now look at the show IP route, we should see that now we have a static route pointing out the tunnel. And if we show MPLS forwarding table, we should now see that we have a TE tunnel that is going towards router 3. Now it doesn't tell us what the outgoing label is here. We need to look at the detail for this. So if we show MPLS forwarding for 3333/32 and look at, or actually no, 3333, we need to say the prefix, 3333/32, and look at the detail. It says label stack is 17. Okay, so we only have one label. The bottom of the stack is implicit null. This is because we are technically the penultimate hop. We are directly connected to router 3 from a logical tunneling point of view. So if we now do a trace to the destination, we should see that we're going to forward over the TE tunnel, and we should be using, let's do a trace 3333, source is loopback 0, or source is our loopback address. We should go out number 17 towards router 2. Now from router 2's point of view, if we look at the show MPLS forwarding table, router 2 is considered to be the midpoint of the tunnel between router 1 and 3 and between XR1 and 3. So we should see 2 entries in the forwarding table, one for each of these tunnels. And the way that it is denoted here is what is the source of the tunnel. So there is a source of the tunnel, which is 1111, and there's a source of the tunnel that is 111111, which is kind of confusing here because notice that there's other entries here that are pointing to these particular destinations. Now the difference being here is that the top 2 do not list the length of the prefix. What instead they're listing is the TE identifier of the head end of the tunnel, or what the source of the tunnel is. Where when we look at 1111/32, that's talking about that particular destination or the forwarding equivalency class that's saying the combination of 1111/32 and this particular outgoing interface are giving us this particular label number in order to reach them. Okay, we can also look at this if we say, show me the MPLS traffic engineering tunnels, and we should see both of these tunnels listed here, where it says that for the tunnel coming from 1111 going to 3333, our role is considered to be the midpoint of the tunnel. Now, it doesn't actually say this here, but you can parse this when you look at the question mark at the end of TE tunnels. You could say, show me the ones that are based on the role as either the head of the tunnel being the source, the tail of the tunnel being the destination, or the middle of the tunnel being not the head, not the tail, and then remote, it means that it could be either the tail or the middle. So if we look at show me the ones that I'm the head end of the tunnel, those are none. Or show me the tail end, there should be none, because likewise I'm not the destination. But if we look at the midpoint, there's 2 tunnels that are going through me. Now the important point of this is that it tells us from router 2's perspective what is its constrained shortest path tree in order to get to the tunnel destination. Where specifically it's from router 2, we're going to router 3's interface, and then we're going to the loopback. So whatever this explicit route is listed here is going to be a subset of whatever the next upstream neighbor is. Our upstream neighbor in this case is router 1. Okay, so let's recap here quickly our full config. On router 1, let's look at the show run, pipe section, MPLS or traffic or ISIS, where globally we said MPLS traffic engineering tunnels. Then at the link level we said, or actually I need to say also interface. Okay, so globally we had MPLS traffic engineering tunnels, and then at the link level we had MPLS traffic engineering tunnels, and we had IP RSVP bandwidth. Globally, under the routing process, we have that TE is on, so which is down here. Traffic engineering tunnels for level 2. Our source address in the database is going to be a loopback 0, and then we have the actual TE tunnel. Okay, so we're coming from our loopback going to router 3. The type is not GRE, type is MPLS TE, and then we're choosing whatever dynamic path that we can use in order to reach the particular destination. Then in terms of the actual routing, when we show IP route, we simply had a static route pointing to the tunnel that was going to the actual destination. Again, from a verification point of view, when we look at the MPLS forwarding table, we should see a label value pointing out the tunnel. When we look at show MPLS traffic engineering tunnels, it tells us was signaling correct, was the path actually valid, and then what is the actual path that we calculated. So from router 1 to router 2 to 3 and then to the final destination.